Chicken speaking. Hello? Hello?
Hello, Dan. We can hear you loud and clear.
Okay, that's great.
Indeed. Welcome.
Yeah.
All right. We have about 80 people congregated locally and virtually. I would like to welcome all of you to the Safnet Birds of a Feather session. This session is being recorded. By now, given that we're halfway through the IETF meeting in Vienna, most of you have seen the note well. Please keep in mind that anything you say is considered a contribution to the IETF and that civility is dearly important to all of us. Everybody who wishes to comment and is locally here in the room in Vienna should load up the Meet Echo Lite tool on their phone. There's QR codes on the chairs, and that allows you to join or leave the queue if you wish to ask a question or express a comment. For the remote participants, make sure that your microphone is muted when you're not talking. So what is Safnet? Safnet, this session is a so-called exploratory birds of a feather session. This means we are not a working group. This is a congregation where we look for other interested parties for feedback from the wider community on the problem of source address validation. And we don't know where exactly this work will go after this session, but this session exists to help us inform on what potential next steps exist and who the people are that are interested to take on this work. Looking at the space that exists currently, there's, for instance, best current practices document 38, but it has proven to be a bit of a challenge in some circumstances. And other initiatives exist such as Manners, but they are a set of recommendations rather than a technology. So in this session, we will hear about technical solutions to improve the ability to combat source address spoofing. We'll start with a background and gap analysis, followed by discussion, which I'll try to moderate to the best of my abilities. And then two potential solution directions are presented, known as Vsaf and Isaf. And at the end of that, we'll again have ample of time for questions and hopefully answers. And with that, I think we can move on to the first presentation. Joel, all good from your side?
That sounds right to me. Let's hand the slides to Dan, and he can present the background and gap analysis.
Okay, I'm ready.
Dan, you have to use the share preloaded slides button on the left-hand panel next to your Q, next to the Q button, and select the gap analysis.
Ask to share the slides.
You control the sharing so that you can page when you're ready.
I think the
Okay.
slides are
Okay. Sorry. Okay. Gap analysis. Share.
There you are.
So can you see the screen, the slides?
Yes. We can see the slides. We can hear you. Go for it.
Okay. So good morning or good afternoon, everyone. Welcome to this Safnet off. I'm Dan Li from Tsinghua University. First, I will present the use cases and gap analysis of source address validation. So we all know that source address validation, or SAVE, is an important problem for the internet. In Vsaf 6 line, 5 line, it makes a very good documentation of the various malicious attacks that may come from source address spoofing, especially represented by reflective DDoS attack. To deal with source address spoofing, network operators need to deploy safe mechanisms on network devices in order to permit traffic with valid source address and block traffic with invalid source address. Since the year of 2014, there is a new wave of interest in safe mechanisms because Manus initiative is calling on network operators to implement safe and expect that the validation should be as close to the source as possible. However, we also know that safe is also challenging. A desired safe mechanism should satisfy the following requirements. The first is accuracy. So we should avoid improper block of normal traffic and should reduce improper permit of spoof traffic as much as possible. The second requirement is incremental deployment. In practice, it is difficult to expect all network operators or all routers to deploy safe mechanism simultaneously. So we hope that partial deployment can also bring benefit. And the third requirement is cost. Although we know that any new mechanism will bring the deployment cost, but we hope that the cost is affordable. So this safe actually is an old problem with a very long history of attention in IETF. As early as the year of 1998, ingress filtering or ACL-based safe was proposed in Vsaf 2267. But its problem is that it requires manual configuration. After that, in 2004, Vsaf 3704 proposed a strict Erpf, feasible Erpf, as well as loose Erpf. However, it is well known that strict Erpf and feasible Erpf has a problem of improper block under asymmetric routing. And the physical Erpf and loose Erpf have the problem of improper permit. The recent efforts on safe mechanisms is SAVI and EFP Erpf. In the SAVI working groups, 6 RFCs were proposed from the year of 2012 to 2017 with a focus on host level safe in access networks or enterprise networks. And about 2 years ago, IETF 8704 proposed the EFP URPF, which is actually an enhancement version of feasible URPF, with the focus of mitigating the problem of strict URPF and feasible URPF in some cases. So why do we need a new intra-domain and inter-domain safe technology? In IETF 5210, the SAVA architecture divides safe into 3 check-in levels, namely access network safe, intra-domain safe, and inter-domain safe. However, SAVI for access network safe is not enough because the number of operators for access networks is very huge. So it is difficult to require all access networks to deploy SAVI simultaneously. When some access networks do not deploy SAVI, we hope that intra-domain safe and inter-domain safe can also help filter spoofing traffic as close to the source as possible, without only dealing with the spoofing traffic and the destination. And for intra and inter-domain safe, URPF-based technology is also not enough. As mentioned, strict URPF, feasible URPF, and loose URPF have improper block or improper permit problems, while EFP URPF does not completely solve the problem. Next, we will use several cases to analyze the gap. The first example, this is an intra-domain network. There are 7 routers. Each router uses one port to connect its subnet and uses the other port to connect the neighboring routers. Now, let's focus on router 7 and assume router 7 applies strict URPF only at the subnet port. So the effect is that if all the other routers in the network make the same deployment, that is, all the other routers apply strict URPF only at the subnet port, that's okay. There will be no problem. However, in practice, we cannot require that all the routers make the same deployment. And let's assume that if only router 1, 2, 4, 7 makes the deployment, and the other routers are in the undeployed area, there will be a problem. So let's see an example. When router 3 sends packets to router 7 by spoofing the source addresses of the deployed area, that is, spoofing the source addresses of P1, P2, P4, then router 7 will improperly permit these packets because router 7 does not enable URPF check-in at its port connecting router 3. Note that it means the sublets in the undeployed area can spoof the source addresses of the deployed area, which will hurt the incentive of routers or operators to deploy safe mechanism. Therefore, it means that applying strict URPF only at the subnet port in intra-domain safe has the improper permit problem. Then we may ask, how about let each router applying strict URPF at all the ports? Okay, let's just use the same figure and the same example. Now, router 7 applies strict URPF at all the ports. But we assume that there is asymmetric routing between router 7 and router 6. Specifically, the routing path from router 7 to router 6 is along the path of router 7, 5, and 6, while in the reverse direction. The routing path from router 6 to router 7 is another path of router 6, 3, and 7. Now there will be a problem. When router 6 sends valid packets with correct source addresses to router 7 through router 3, when router 7 checks the incoming interface of these packets by looking up its local FIB, it will find that, okay, the incoming interface does not match the outgoing interface of the FIB. So it will improperly block these packets. So it means that in this case, applying strict Erpf at all the ports in intra-domain sieve will have improper block problem. As a whole, no matter whether we apply strict Erpf at the subnet port or apply strict Erpf at all the ports, there will be either improper permit problem or improper block problem for intra-domain network. Okay, then let's turn to the intra-domain case. In this figure, there are 5 ASs, S1, 2, 3, 4, and 5. And then let's pay special attention on S4. Now, S5 is a peering AS of S4, and S1 and S2 are 2 customer ASs of S4. S3 is a customer of S1 and S2 with a multi-homing connection. So due to the no expert community, when S3 propagates its roots of the prefix P3 to other domain of the network, it only propagates along the path of S3, S2, and S4. And it does not advertise its roots along the path of S3, S1, and S4. Okay, now let's check the safe mechanism for S4. Assume that S4 runs strict Erpf or feasible Erpf or EFP Erpf with algorithm A and its 2 customer ports. Now, the safe rule at S4 is that the packets with source addresses of P3 can only arrive from S2. But now, S3 may send packets with valid source addresses to S4 through S1. For these packets, S4 will improperly block them. So it means that in intra-domain sieve, strict Erpf, feasible Erpf, or EFP Erpf with algorithm A will need to improper block problem. Okay, then we may ask that, how about S4 choose other Erpf mechanisms besides, okay, strict Erpf, feasible Erpf, and EFP Erpf with algorithm A? There are 2 other Erpf mechanisms. One is loose Erpf. So loose Erpf will cause significant improper permit. And EFP Erpf with algorithm B proposed some enhancement on that. The idea of EFP Erpf with algorithm B is that, okay, S4 configures its safe rules and the customer ports like this. S4 will generate an allow list containing source prefix of the customer cone. Okay, that is including S1, S2, and S3, and applies the allow list to all its customer ports. The benefit of EFP Erpf with algorithm B over loose Erpf is that the packets from S4's customer cone cannot spoof the source addresses of the outside ASs, which is finer grained than using loose Erpf. Because by using loose Erpf, the customer cone actually can spoof whatever source addresses. Okay, now we can observe that there is another problem. That is when the packets from S1 and S2 spoof the source addresses of each other, S4 will improperly permit these packets because S4 has no capability to distinguish the packets from its customer ASs. Generally, we can conclude that loose URPF or EFP URPF with algorithm B in interdomain sieve may lead to improper permit problem. Okay, so we find that there are improper permit or improper block problem for both intradomain network and interdomain network by using existing URPF-based technologies. Then we ask a question, what is the root cause? We think that the root cause of the improper block and improper permit problem for URPF-based safe mechanism is that URPF is a load-level technology. It means that they all leverage the local FIB or RIP table of routers to decide the incoming interface of packets, which may not match the real data plane forwarding path. So to solve this problem and achieve accurate sieve, we may need a network level technology instead of the node level technology. We hope that a network level protocol can help build an independent and accurate sieve table in each router, which follows the real data plane forwarding path. And compared with strict URPF, this sieve table is different from the FIB table, so the improper block problem under asymmetric routing can be avoided. And compared with feasible URPF, loose URPF, or EFP URPF, the sieve table is fine-grained, so the improper permit problem can be avoided. There are also some requirements for designing such a network level safe protocol. The most important requirement is accuracy, because this is the most important problem of URPF-based technologies. So we hope that the new protocol can help avoid improper block and reduce improper permit as much as possible. And there are also some other requirements, such as high scalability, which means that the protocol should not cause too much computation and communication overhead. Incremental deployment, which means that only partial routers in the AS or only partial ASs in the internet deploy the new protocol. There will also be overall scheme compared with the URPF-based safe, as well as the high security, which means that the integrity and security of the protocol messages should be guaranteed. And our basic idea to satisfy all the requirements above is that we can discover the real data plane forwarding path based on hop-by-hop prefix notification and generate safe tables in routers along the notification path. Okay, then I will make a brief summary of this talk. Intradomain and the interdomain sieve is an important and unresolved problem in our community, although it is an old problem. And in both intradomain and interdomain scenarios, URPF-based safe mechanisms have either improper block problem or improper permit problem. And we argue that the root cause of URPF-based safe mechanism is that it's a node-level technology, and it depends on routers' local FIB or RIP for checking the source address. And to achieve accurate sieve, we hope that a network-level protocol can build an independent and accurate safe table in each router, which follows the real data plane forwarding path. Okay, that's all the stuff. I'm glad to answer any questions. Thank you.
Thank you so much. I see that the queue immediately filled up with number of participants. This is good news because it means that people are paying attention to what you were saying. First up in the queue is Ted Lemon.
Hi. Yeah, Ted Lemon. Can you go back 2 slides or maybe 3 slides to the last diagram?
Three? No.
To the
Okay.
last diagram. One more.
Last diagram.
This one.
This
yeah.
one?
So
Okay.
Ted, please move close to the microphone.
oh, sure. Sorry.
Perfect.
So I had a couple questions. One is oh, sorry, not this diagram. It's the one with the ISP with
Next
the,
one.
and one more.
Inter-AS.
Yes, here we go. Okay, so in this model,
This one.
and either one of those is fine. In this model,
Okay.
In order for SAV to work, it would need to be the case that that you trust the routers, the AS1 router, the AS2 router, to enforce the behavior, basically to enforce the address validation. Is that correct?
Yes.
So in other words, if the problem that you're stating here is that if a device on the customer network sends a packet to the AS1 router, the AS1 router that's got a bogus source address, the AS1 router is trustworthy. You trust the AS1 router to block that packet. Is that right?
So now you mean the blocking behavior and AS4, right? We still focus on the blocking behavior and AS4, right?
No. So the
Or
problem
no,
that you,
or
the problem
AS1.
that you were, yeah, the problem that you were describing here is that it's possible for someone in AS1 or AS2 to spoof packets from AS3, right?
Yeah, maybe in this case more exactly is that we want to S4 cannot distinguish okay the S1 and S2 to spoof
Right.
the address of each other. S3 actually is S1 and S2's customer. If S1 and S2 deploy save mechanism, maybe this kind of spoofing can be detected and avoided.
Right. So the problem that I'm asking about here is I'm trying to understand the trust model, because so AS4 doesn't know where the packet came from, right? If the packet came from AS3, it's going to look roughly the same as if the packet came from AS1, regardless of its source address. Or for example, it might even come from AS2, and still AS4 is going to have no way to tell where that packet came from because there's nothing in the IP header to authenticate it. So therefore, part of the trust model here is that, I think, if I understand you correctly, is that you're assuming that the routers are trustworthy, that AS1 is going to reject a bogus source address from its own internal network, and that's part of the trust model. Is that right?
Actually, it's like this. Actually, because either Erpf or this kind of save mechanism, actually they just make the source address checking based on the incoming port. So for the incoming port, actually they can only judge the correct direction of this of this source address. But if there is some spoofing between the ASs along the same path, actually they cannot distinguish between them. But the key is that if we can do this kind of port-based direction checking, even though there is some source address spoofing along the path, actually we can narrow skip and help us trace back the source address spoofing.
Okay, so you're able to cast blame essentially.
Yeah.
Okay. All right, that helps. Yeah, the reason I'm asking about this is because the trust model here is unclear, and I think it's actually worth documenting the trust model when you're talking about this, because otherwise, you know, when I look at this, I think, well, your solution sounds like it's complex and wonderful, but doesn't actually solve the problem because you still have the trust problem. But so saying why that model actually makes things better is important. And then the other question that I had is just that, you know, and which actually ties back to what you just said, is that in this scenario, AS4 is the ISP, AS1, 2, and 3 are customers. So the enforcement path here is different than it would be if these were all independent, right? And it's worth talking about that as well, I think. So that's all I wanted to say. Okay. I mean, I think this, you know, I don't have any objection to any of this stuff. I just want to make it, I just wanted to ask about the trust model because I think it's really important to talk about that as you're documenting this.
Yeah, actually, this kind of trust model is also the trust model used in Erpf. All these kind of incoming port-based safe mechanisms have this same trust model. Yeah, maybe we can just make them more clear. Okay, thank you.
Small interjection. I think it's good if participants coming to the microphone raise 1 point at a time and then rejoin the queue. Next up, Bo Tao, please. Bo Tao, I'm not sure we can hear you.
Hello?
Yep, I can hear you. Please go ahead.
I have a question. I saw you analyzed the improper permit problem of the enhanced feasible past URPF in the interdomain case and mentioned two algorithms. You called it algorithm A and algorithm B. Could you please tell me what is their difference?
Okay. So you mean the difference between the two algorithms of EFG RPF, right?
Yes, yes.
Okay. Actually, these two algorithms were proposed in RFC, I think 8704. So the difference is that for algorithm A, it just applies an individual allow list to each customer port, maybe just based on the routes received by that port. So since these customer ports are just configured different independent allow list, so it may have improper block problem when one customer port does not receive any route for an AS, just like the scenario we used, I think, in this case, in this slide. And for algorithm B, it just applies the same allow list to all the customer ports. And it will also allow the packets with source addresses of all the customer ASs if they come from the customer interfaces. So that this is algorithm B. So by algorithm B, it can avoid the improper block problem in algorithm A, but may have improper permit problem because the ASs in the customer code can spoof each other. So if you have more interest, I think you can refer to the RFC 8704. It has a very detailed description. Yeah, thank you.
Okay, thank you very much.
Next up is Giuseppe. My apologies.
Hello?
Fiocola?
Hello? Can you hear me? Can you hear me?
Can you speak up a little bit louder, please?
Can you hear me? This is Giuseppe.
Thank you.
Okay. Yeah, I have a general question. Yeah, thank you for the presentation.
As you mentioned the need for a network level protocol to achieve accurate SAV, what is the deployment scope of network level?
Sorry?
Maybe I can I go ahead?
Go ahead,
Because
Giuseppe.
there was an overlap.
People talking. I took care of that. Go ahead, Giuseppe.
Okay. Yeah, thank you for the presentation. I have a general question. So you analyze basically the improper behavior of URPF and the root cause also for this inaccuracy. And you state that the cause is caused by local FIB and RIB of routers. So after that, you propose a network level protocol for discovering the real data plane path, right? So instead of, because we have to pay a cost for this discovery, for this network level protocol. So I'm wondering if if we can consider multiple feasible paths to apply safe rules can also work, or you did think about that, or?
Oh, okay. I get your question. I think in our mailing list, maybe Yari has asked similar questions. That is okay. If we just make this probing of the real data plane path, of course we will pay additional cost. And an alternative way is that how about we just use some feasible paths, and all the packets arriving along the feasible paths will be permitted. Otherwise, they will be blocked. Actually, this is the same idea used in feasible Erpf. But this idea actually also has improper block or improper permit problem, because when the packets come from the path that is beyond the feasible path, just like the example we use in the interdomain scenario, actually it will cause improper block, because maybe AS does not learn the routing path of the actual data plane forwarding path because of some routing policies. So this will cause improper block problem. And this kind of feasible path solution will also need to improper permit problem, because this is very straightforward, right? Because there are multiple feasible paths, but the real data plane forwarding path is only one. So of course there will be some improper permit problem. Okay, thank you for this question.
So thank you. So yeah, it does not solve all the problems. So maybe it can help, but without solve all the problems. Thank you.
Okay, thank you.
Next up, Tim Donna.
Hello.
Yep,
Yeah.
can hear you.
As you mentioned the need for network level protocol to achieve accurate SAV, what is the deployment scope of the network level SAV protocol? For example, EFP-URPF requires communication between border routers in the AS.
Okay, you mean the deployment scope of the network level safe protocol? Yeah, actually in EFP-URPF, it indeed requires some communication between the border router in the AS.
The deployment scope of the network level SAV protocol.
Yes, I think I get your point. But in EFP-URPF, although there are some communication between the border routers in the AS, but if we just abstract the AS as a single node, actually it's still the information exchange within the single node. So we still regard that EFP-URPF is a node level technology. But we want to just propose a network level protocol. The concrete idea of which will be presented in the next presentation. But generally, in the intradomain level, the network level protocol will be run between routers in the AS. And on the interdomain level, this protocol will be run between different ASs. So these are just network level protocols. And we just see that the Erpf is just a node level technology, right? So they only achieve SAVE based on the local FIB and RIB. So we just want to use this network level protocol to generate more accurate SAVE tables to overcoming this problem. And of course, for this deployment scenario, we should consider incremental deployment. Yeah, I think that's the deployment scope of this protocol. Thank you.
The next person who will speak is Tim Donna. Nobody else.
Hello. I have a question. For the interdomain case, you only mentioned the safe rules in the customer ports, but not mentioning the provider and peer ports. Can you explain the case of provider and peer ports?
Okay, for the inter-domain case, yeah, we just discussed the customer ports because actually in current practice for the peering ports and provider ports, they just suggest using new CRPF, and even in IETF 8704. They just made some improvement on the safe mechanisms on the customer ports. For peering ports and provider ports, this RFC actually also suggests using new CRPF, because new CRPF will lead to a lot of improper permit problem. So we do not discuss these problems in detail. Thank you.
Okay, thank you.
Jared.
Yeah, I was trying to figure out if I was next. So I think you've partially answered my main question here, which is your goal is, and this is going to be in the next deck, is to describe a protocol that will, I guess, publish a list of IP addresses that should be, that should be able to be permitted on a link.
Mm-hmm.
Okay, and so something to describe that network topology or something. And then I have a comment on that, which is it's been historically incredibly hard to get not only customers, but ISPs to publish, who their customers are and what address space that they use or want to be used. And that has been an incredibly hard operational task to go and get done and to describe that topology without it exploding into basically a full list of all IP address space on the internet.
Thanks for your question. Yeah, actually, for this network level notification protocol, maybe there is some sacrifice on the privacy issue. That is, maybe some ASs will just expose some of its routing policy, its business relationship, because it will just explicitly send out the notification message. So this message will just leak some privacy issue. But generally we think that it is a trade-off between privacy and security. So if we want to just use an accurate method to prevent this kind of source address spoofing, maybe this kind of privacy issue, we can just make some kind of sacrifice. But of course, we can just design more mechanisms to limit this impact. Maybe we can discuss more details on this point in the meeting list. Okay, thank you for this question.
Next up, Jari Arco. We cut the queue so that after Jeff Haas's comment or question, we can move on to the presentations about the protocol proposals. But back to you, Jari.
Yes, thank you. This is an interesting discussion and important problem. I've been trying to think about the root cause and what are the actual fundamental issues here. And I actually identified 4 things. Root cause number 1 is that you have information that you could base decisions on, but you don't actually use it or don't use all of it. And as an example, perhaps you have like a full network topology model in your memory based on what you learned from the routing protocols. You could use that to make decisions on what addresses are okay or not okay. So for this case, the answer is just use a better algorithm or use an algorithm to begin with. Okay, so that was 1. Number 2 is that you don't have information. Let's say your routing protocol doesn't provide everything that you would need, or for some other reason you don't have information that would enable you to make these decisions on source address validation. And then the answer obviously is provide more information, either in the form of a new protocol or some extensions of existing ones. I think Igor, who's after me on the queue, had some proposal on the list about that. Third option is that, or third root cause is that you have information about the feasible routes, but you don't have information about the actual ones that are being used at this time. And I guess here you have to decide what you want. Like, you could be satisfied with some improper permits and just look at the feasible routes. Then you have a simpler solution, or you create a more complex solution that costs more, but you catch more issues. And root cause number 4 is kind of variation of the third one about this actual paths versus feasible paths. And there's an issue that if there's a change somewhere else in the network, when do you actually learn about that? And if you think about it from the point of view of the node that has a change for some reason, like a link is added or removed, they could either inform everybody, and after everybody's been informed, start forwarding packets to the new direction, or they could just make an immediate change and in parallel inform everybody about the change. But you could have a situation where there's a short period of time where you as a receiving entity appear to get packets from a direction that they should not come from, because you have the network hasn't really coordinated itself entirely yet. And I don't think that's actually a solvable problem. You either have to wait or accept some packet drops or some accepting of packets momentarily. And this also gets me somewhat confused about the network level discussion that we had, because we can talk about the network level solution, but we still have individual nodes that have to make decisions and are not exactly synchronized to everybody else on the same instant because of speed of light and such. That's it. Thank you.
Okay. Thank you, Yari, for the comments. Actually, we already discussed some of your questions in the mailing list. I think, I'm highly appreciated for your very deep think of these issues. Generally, I think for safe mechanisms, we can just maybe we can come up with some mechanism which is very easy to deploy. The cost is very low, but maybe there will be some inaccurate inaccurate decision, improper permit or improper block. Or the other extreme is that we just to achieve accurate decision, we will pay the cost of the new protocol, the network level protocol. So my design philosophy is that actually for today's internet, actually
It seems we have a loss of connection. Unexpected.
And fairly serious. It's our primary presenter for the next deck that seems to have lost his connection. We lost slides. We also lost audio from Dan Lee, and we lost connectivity from Dan Lee.
Lost. Can you hear me now?
Yes.
Okay.
Looks like you're back, and your deck is coming back too. Go ahead.
Yeah. I think I just quickly answer Yari's, just respond to Yari's comments. Just my design philosophy is that I want to that first we should satisfy the performance requirement. That is to improve the accuracy. And under this assumption, we will just try to reduce the overhead, just limit the overhead as much as possible. So I personally prefer this direction of solution. And for the final comment from you is that okay, when there is during the convergency period, okay, there we have to pay the cost of okay, the packet drop, just the improper block, something like that. I think yeah, it's just the similar as the routing protocol. So in any kind of routing protocol, during the converging period, there may be loop, right? And if there is loop, this kind of a temporary loop will also cause packet drop. Okay, so I think that this for source address validation actually for this question it's very similar as the routing the routing protocol. So we just want to design several ways just to try to mitigate this problem instead of still paying the cost of general improper block or improper permit. So I think this is a very interesting debate, and we can also explore more in our mailing list. Thank you.
Okay, we've got 2 more speakers with questions. I want to get those questions. Dan, please make your answers a little bit shorter. We're running late on time, but I want to get through these next 2 questions. Thank you.
Okay, thank you.
Can you hear me?
Can you say some
Hi, Igor.
another sentence?
Yeah. I can hear myself. All right. Okay, good. Thank you. So I have a comment and a quick question. So the quick comment is that, in my view, the reason we're having the discussion, the reason we're having the problem, is that all the current methods are using what is effectively reachability information, BGP, as a substitute for allowed forwarding path for source address validation. And it's just not the most accurate signal, and that's why we're having problems. The question I have is, what do you think is acceptable cost of any sort of source address validation solution relative to the current cost of forwarding packets? So essentially, like, how much cost do you think the industry will be able to bear to enable this extra level of security?
Hi, Igor. Am I lost or no?
I think you are up, Dan.
Oh, no audio?
We can hear you, Dan. Go ahead.
So Igor, so I'm actually I did not quite exactly get your question. Yeah, I get your comment, but your what's your exact question about this?
The question I have is, what do you think? I mean, SAV will add cost to the forwarding path. What do you think is a reasonable cost that the internet, the industry will be able to bear, like relative to the cost of forwarding packets? Is it like twice as much hardware, 3 times as much hardware, like in terms of ASIC per packet?
Okay. Okay. Now I get your point. Yeah, I think maybe these issues will be described with more details in our next presentation. But generally, I think for the cost, we should still just divide this protocol into inter-domain and intra-domain. So for inter-domain stuff, maybe we can just extend the capabilities of BGP to help carry more information required for this the data plane path notification or discovering. And for intra-domain part, because the scope is smaller, I think maybe we can just design a new protocol to ask routers to exchange more information with each other. Generally, I think that the cost for discovering the real data plane forwarding path should not be higher than routing protocols. We just want to leverage existing routing protocols such as BGP or design new intra-domain routing intra-domain network protocols, which just shares the same complexity of routing of intra-domain routing protocol, but not greater than that. That's my general thinking about the cost we should pay for this kind of source address checking. Because actually, this is just a different part. Routing protocol is for destination, and this safe network protocol is for the source address. So that's just two counterparts. So I think their complexity should be similar. Thank you.
Wai Kiang Chen, it is your turn to.
Hello. Yeah. So thank you, Chair. I think it's very important to operators to avoid the improper block and permit. So I think this direction is valid. I have a very quick comment. I don't think I need some response. So you know, operators network is very large, and the number of the nodes, such as in the backbone network, maybe reach thousands. So I guess it's reasonable that put the being suitable for the large scale network deployments should be important requirements when we design the network live protocol. So thanks.
Okay, thank you.
All right, the next presentation is about, I think we start with Vsaf.
Yeah, that was right. Yeah. Okay. So,
Go ahead, Dan.
It seems I cannot grant the permission.
Oh, can you hear me?
We can hear you.
Yeah, yes, Lan Cheng, but we're trying to get Dan to switch. So I can't tell who's got slide control at the moment.
There we go.
Oh.
There we are on the right slides.
Okay. Hello,
You're
everyone.
doing the presentation, Lan Cheng. Sorry, go ahead.
Oh, thank you. Hello. I am Lan Chengqin from Tsinghua University. I'm going to introduce the DSAVE framework, validating source addresses via save tables generated by a distributed control plane protocol. SAVA divides SAVE into 3 different checking levels, and SAVE is proposed to achieve SAVE at access networks. It is only fully effective when globally deployed. However, it's impractical to expect all access networks to deploy SAVE simultaneously. If an access network doesn't deploy SAVE, spoofing traffic from it should have a chance to be blocked before arriving at the destination host, and Manners requires operators to deploy SAVE as close to the source as possible. As we described in the gap analysis, existing intra- and inter-domain SAVE technologies may lead to improper block or improper permit problems. So, to guarantee accuracy, a network-level protocol is necessary. DSAVE framework depends on a distributed control plane protocol to generate accurate safe table instead of using Erpf. Introducing a network-level protocol can bring additional overhead, so it's important to improve the scalability of the protocol by limiting the computation and communication overhead. With an accurate safe table, the router can verify the authenticity of the source address by checking the incoming port of the packet. And packets with spoofed source addresses will be blocked, and packets with legitimate source addresses will be forwarded based on safe table. So the basic idea of DSAVE protocol is to discover the real data plane forwarding path by hop prefix notification and to generate safe tables in routers along the path. DSAVE protocol is separated into an intra-domain part and an inter-domain part, both sharing the same high-level idea. Here, we list some terminologies. The node is a router in intra-domain DSAVE or an AS in inter-domain DSAVE. The prefix notification means the process by which a node notifies the incoming direction of its source prefixes to all the other nodes in the network. And during prefix notification, each node conducts one of three operations. Message origination means a node generates original notification messages. Message relaying means a node generates relaying notification messages after receiving a notification message. Message termination means a node terminates the received notification message. The DSAVE notification message contains two main fields, source prefix field and propagation scope field. For source prefix field, it contains the source prefixes of the node. When receiving a message, a node generates safe rules for the source prefixes, and this field will remain unchanged during the prefix notification process. For propagation scope field, this field contains a list of destination prefixes which take the neighboring node as the next hop from FIP. It is used to discover the real data plane forwarding path and change hop by hop during the prefix notification process. Here, I will use an example to illustrate the workflow of DSAVE. There are 7 nodes in the network, and I'll show the process of prefix notification for P1. The processes of prefix notification for other prefixes are similar. Let's say node 1 conducts message origination since P1 is the source prefix of node 1. From node 1 FIP, P2, P4, P6, and P7 take node 2 as the next hop, so node 1 generates an original notification message to node 2. In the message from node 1 to node 2, it carries P1 in the source prefix field and carries P2, P4, P6, and P7 in the propagation scope field. Besides, from node 1's FIP, P3 and P5 take node 3 as the next hop, so node 1 generates an original notification message to node 3, carrying P1 in the source prefix field and carrying P3 and P5 in the propagation scope field. We can also see node 7 is another neighboring node of node 1. However, from node 1's fib, no prefix takes node 7 as the next hop, so node 1 doesn't send any notification message to node 7. Then, when node 2 receives the notification message from node 1 at port 2.1, it first generates the save rule for source prefix P1. That is, it specifies the incoming port 2.1 as the valid incoming port.
I was just watching, but I do have a question.
As a valid incoming port for source prefix P1. Then node 2 checks.
Go ahead.
Then node 2 checks the propagation scope field of the received message. The propagation scope field of the received message contains 4 prefixes. They are P2, P4, P6, and P7. P2 is the source prefix of node 2, so node 2 does not to process this prefix. While from node 2's fib, P4 and P6 take node 4 as the next hop, so node 2 conducts message relaying and generates a relaying notification message to node 4. The message from node 2 to node 4 carries P1 in the source prefix field and only carries P4 and P6 in the propagation scope. It's worth noting that P6 may take different next hops because of multipath routing. So from node 2's fib, P6 and P7 take node 7 as the next hop. So node 2 conducts message relaying and generates a relaying notification message to node 7, carrying P1 in the source prefix field and carrying P6 and P7 in the propagation scope. Next, when node 4 receives the message from node 2 at port 4.1, node 4 first generates the save rule for source prefix P1. It then checks the propagation scope P4 and P6. From node 4's fib, P6 takes node 6 as the next hop, so node 4 conducts message relaying and generates a relaying notification message to node 6, carrying P1 in the source prefix field and carrying P6 in the propagation scope field. Similarly, when node 7 receives the message from node 2 at port 7.1, it generates the save rule for source prefix P1, and then it checks that P6 takes node 6 as the next hop, so node 7 conducts message relaying and generates a relaying notification message to node 6, carrying P1 in the source prefix field and carrying P6 in the propagation scope field. In this way, node 6 will receive two notification messages from node 4 and node 7 at different ports. Therefore, node 6 can discover the multi-parting routing, and it specifies 2 valid incoming ports for source prefix P1. Then, node 6 conducts message termination because the propagation scope only contains prefix 6, and prefix 6 is the source prefix of node 6. When node 3 receives a message from node 1 at port 3.1, it also generates the save rule for source prefix P1, and then from node 3's fib, P5 takes node 5 as the next hop, so node 3 conducts message relaying and generates a relaying notification message to node 5. The message from node 3 to node 5 contains P1 in the source prefix and carries P5 in the propagation scope field. When node 5 receives the message from node 3, it generates the save rule and then conducts message termination because the propagation scope only contains P5 and P5 is the source prefix of node 5. At this point, the whole process of prefix notification for P1 is over. During the prefix notification process, each node generates accurate save rules for P1 and receives only one message, except for multipath routing. We have considered two DSAVE update models. For periodic update, each node generates original notification messages periodically. For triggered update, when routing state changes, the node generates original notification messages to add updated save rules or delete outdated save rules for the affected nodes. Following the principles of existing routing protocols, we suggest intra-domain DSAVE supports both periodic update and triggered update, while inter-domain DSAVE only supports triggered update. As described in the gap analysis for intra-domain save, applying strict URPF only at subnet port may have improper permit problem, while applying strict URPF at all ports may have improper block problem. But if router 1, 2, 4, and 7 run DSAVE in the deployed area, subnet 1, 2, 4, 7 cannot spoof each other, and packets from subnet 3, 5, 6 with spoof source addresses of P1, P2, P4, P7 will be accurately blocked at port A, B, C, D, while strict URPF may have improper permit problem. Moreover, legitimate packets from subnet 3, 5, 6 will be accurately permitted at port A, port B, port C, and D, while strict URPF may have improper block problem. Overall, compared with URPF in the intra-domain save, if we deploy DSAVE in the deployed area, subnets within the deployed area cannot spoof, and subnets in the undeployed area cannot spoof the source addresses of the deployed area. For inter-domain save, strict URPF, physical URPF, and EFP URPF with algorithm A may have improper block problem, while loose URPF and EFP URPF with algorithm B may have improper permit problem. Deploying DSAVE and AS1, AS2, AS3, AS4 can generate save rules for P1, P2, P3, and P4. In this way, AS1, AS2, AS3, and AS4 cannot spoof each other, while EFP URPF may have improper permit problem. Besides, packets from AS5 with spoofed source addresses of P1, P2, P3, P4 will be blocked at port A, while loose UIPF may have improper permit problem in this case. Overall, compared with UIPF in interdomain sieve, ASs within the deployed area cannot spoof each other, and ASs in the undeployed area cannot spoof the source addresses of the deployed area. Here, we have some open questions about to further improvement of DSIV. For accuracy, the key of DSIV is to discover real data plane forwarding paths, so any factor that affects forwarding should be considered. For example, policy-based routing like static routing or ACL redirection may change the data plane forwarding path of SIF table. So how to handle this problem? For scalability, containing a long list of IP addresses in source prefix field and propagation scope field is costly. Can we compress DSIV protocol messages? For convergency, when updating, there may be a gap between the change of SIF table and the update of SIF table. So how to avoid improper block in this time keep? In fast rerouting, when a link fails, the router can select a backup forwarding path immediately. How to handle resultant improper block since the SIF tables of downstream routers do not learn the backup forwarding path. For incremental deployment, how about multiple disconnected deployed areas? For security, what's the threat model of DSIV protocol messages and how to address? For privacy, in interdomain DSIV, an AS will tell its local routing policy information to other ASs. Is it a leak of privacy? Thank you. We are glad to explore more suggestions and more solutions.
Thank you very much. First up in the queue is Nalini Elkins.
Hi, Nalini Elkins, Inside Products, and I'll bring up one issue at a time. If you can go back to I think the very, very first slide that you had. I'll continue talking while you're doing that.
Which slide?
Yeah, I think very, very beginning one. Yeah, keep going back. Keep going back. Back. Yeah. Maybe one more back.
Nalini, lean into the mic, please.
Okay, can you guys hear me?
There,
okay.
Yes.
Okay. All right, well, so whatever. So, okay, it seemed to me, okay, one, don't get me wrong, this is a very good idea, I think, and necessary, and I think we're happy to work with you. But I think there's a couple of fundamental flaws, and I'll bring them up one at a time, let other people talk. First fundamental flaw, I believe it depends on hop by hop header and being accurate and not spoof. And so if the hop by hop extension header is bad to start with, well, there you go. And we are happy to work with you on that because we have an idea ourselves, because we have another IPv6 extension header that we need to be extremely accurate. So if you want, we can explore collaboration. But let me see what you think about that.
That's great. Yeah, we are looking forward to collaboration with you. Yeah.
Okay, so then I'll go on and bring another question, let other people talk.
Thank you. Next, Antoine Fressancourt.
Yeah, you nearly got it right.
Thank you.
So I have a question. The slide is perfect. regarding the propagation scope. Here, if I understand well, you build the propagation scope with the information that are in the fib of the node. Did you explore the possibility to have a propagation field that is built by each hop? For instance, you have a message where you have a source field that you certify, and then the next node is using the message from that is coming from the originating node, populate the propagation field and relay it to its neighbors. So you build the propagation scope field hop by hop, and you can then verify the path completely rather than just the source.
Do you mean how to discover the real forwarding path from original to the destination?
It may be a method for doing that, but in fact, you can use this, build this propagation field and spread the message to all the neighbors, so you can discover all possible paths and not the paths that are used for relaying the traffic, maybe.
The voice is very low. Actually, can someone repeat this question more louder?
I will try to speak closer to the mic if you want. My question was regarding the propagation scope field. Do you think that it could be an idea, rather than building the propagation field from the information that are in the fib, to build it hop by hop with you originate a message with only the source prefix field, and then the neighbor puts the prefix in the source prefix field message they received in the propagation scope field before relaying the message to their own neighbor, and it goes on until you propagate the message in all the network?
Actually, the reason that we use the current way to hop by hop notify the source prefixes by using the propagation scope is just want to minimize the number of protocol messages during this whole process of prefix notification. So another possible way is that we just carry just some destination addresses in the packet head in the payload, and just probe those paths. It will bring much more protocol overhead. So yeah, actually we use the fib for the notification because we want to discover the real data forwarding path, because the real data plane forwarding path is determined by the fib table.
Okay, thank you.
Okay, thank you.
Next up, Linda Dunbar.
So I have a couple of questions. First is, do
Linda,
you also
one question at a time?
Yeah. Do you consider using the ACL as well?
Yes.
Okay, so the ACL, right? They validate source address, destination address, and also the port number. So do you have an analysis like showing different ways incorporating with ACL?
Sure. We do have some solutions for ACL. Yes, you are right. ACL redirection may check source address, destination address, or port number. Yes, and we think DCL can use the control plane routing information to generate notification messages along policy-based forwarding paths, including ACL redirection paths or other, for example, tunnel path.
Okay, so if the tunnel is used, do you validate only the tunnel address, endpoint address, or do you validate the address carried inside the tunnel?
Only at the point and at the incoming port.
Incoming port, okay. Thank you.
Next up, who are Imo Chen?
Yeah, Huaymo from Future Network. I just have a comment. So you propose two methods for message propagation. One is one shot. The other model is periodically originate and relay the messages. I think that if you use BGP protocol and then one shot is okay because you don't need to do the refresh every half hour, every 1 hour. So if you use the BGP, if you use the IGP, then those are already in the protocol itself. Looks like you are using BGP, and then we don't need to do the periodical message origination and the propagation.
Okay. For intra-domain, I think IGP cannot learn the real forwarding path because nowadays static routing and ACL redirection are common in intra-domain. They also influence the forwarding path, but other routers cannot learn this information through IGP, right? So to achieve accurate save in any scenario, a network level protocol is necessary. And in DSAVE, a node can send prefix notification to other nodes. And as for, you said we can use BGP, right?
Yeah, I think that in the previous presentation by Dan Lee, so it looks like you're using BGP. So once you use BGP, you don't need to do periodical updates, right?
I think inter-domain DSAVE only supports triggered update, and if you mean we can use BGP to send the prefix notification, it's about a protocol selection question. Now, protocol selection is an open question. We hope to get more suggestions and reviews, and whether we design a new protocol or extending existing routing protocol, for example, BGP, is okay. It's an open question.
Thank you. Next up, we have 3 more minutes, then we need to jump to the next presentation. So the next questions need to fit in 1 minute. Meng Xiao Chen, your turn.
I'm from HCC. I have one question. In your analysis of scalability of DSAV, you see that in most cases, a node receives only one protocol message originated from every other node. Could you explain why?
Okay, you mean the scalability issue, right? Okay, we can go back to the example. In the process of prefix notification for P1, we can see node 1 is checks its FIB table, and from node 1's FIB, from node 1 fib, it finds node 2 and node 3 are two next hops in its fib. Therefore, it takes node 2 as a next hop, and it generates an original notification message to node 2. The message generated from node 1 to node 2 carries P1 in the source prefix field and carrying P2, P4, P6, and P7 in the propagation scope. And for the next hop, node 3, from node fib, P3 and P5 take node 3 as the next hop, so node 1 generates an original notification message to node 3, and the message from node 1 to node 3 carrying P1 in the source prefix and carrying P3 and P5 in the propagation scope. But for the neighboring node 7, although it is the neighbor of node 1, however, in node 1's fib, no prefix take node 7 as the next hop, so node 1 doesn't send any notification message to node 7. So in this way, node 1 only sends one message to each neighbor, and during the propagation, each node only receives one message, and they can generate accurate zeros. Thank you.
I think we ran out of time, so we need to move on to Isaf. Anybody that's still in the queue, please send your comments to the safnet@ietf.org mailing list so that we can, despite not being able to handle the questions right here, right now, still take a look at that input. My apologies. All right, next up, Isaf. Xiao Liang Wan is maybe how you pronounce it. Is your audio working? Can you say something, please? It might be easier to use the preloaded slides. It's the second button on the left, next to, just left of the one you press to share your screen. So stop the screen sharing and then go, yeah. Oh. Perfect. Now all we need is audio. Can you say something into your microphone, please? I can see slides.
Xiaoliang, we can't hear you.
Okay, can you hear me and see this screen?
We can hear you. Please speak up a little bit.
Okay. Good evening and good other times, everyone. This is Yang Guo, and my presentation starts from here. I will show you the Isaf framework, an end-to-end data plane approach for source address validation. The Internet Protocol, IP, is the most fundamental building block of current network architecture. This protocol allows us to allocate address to different devices for recognition and deliver packets on the Internet. However, it provides no explicit notion of packet-level authenticity. Such a weakness allows malicious actors to spoof IP packets and launch a wide variety of attacks. For example, DHCP spoofing, DNS reflection DDoS, and TCP SYN flooding, to name just a few. However, as the main defense mechanism, the real-world deployment of source address validation in the past decades is far from being satisfactory. There are many reasons for this, and we believe one potential improvement direction is to strike a better balance between security benefits and scalability. Therefore, we set three main design goals for Isaf. First, having clear and consistent security benefits in various scenarios is the biggest deployment incentive for source address validation. Second, scalability from partial to large-scale deployment need to be supported. Thirdly, provide flexible verification capability, flexible requirements for source address validation granularity for different application scenarios need to be achieved. Let's start with a general overview of how Isaf works. The source AS and the destination AS directly form an end-to-end packet tag synchronization, after which the packet from the source will carry the legal packet tag and be received by the destination. Spoofed packets don't have the tag and are marked as suspicious by the destination and are either processed further or dropped directly. To implement this design, Isaf will require both a data plane and a control plane. Within an AS, the control plane will be implemented through a device called the AS Control Server, or ACS, and the data plane will be implemented through an AS board router, or ABR, where the ABR is responsible for adding, checking, replacing, and deleting tags for all upstream and downstream traffic. And the ACS is responsible for providing the ABR with the information needed for the relevant tag operations, such as the legal prefix to tag mapping. The controllers of different AS need to work together to maintain a trusted alliance and achieve consensus on the information required for tag operations within the alliance. This requires the support of existing network infrastructure, such as the mapping between AS number and IP prefix provided by RPKI. With the packet tag mentioned above, Isaf can guarantee a clear security gain within the deployment and guarantee the authenticity of the source address of the traffic that has passed the tag check. Instead of only checks its own traffic. On the other hand, Isaf is designed with AS community to provide a good scalability. So the overhead of establishing a universal end-to-end trust and tag verification mechanism at the internet scale is hardly acceptable. With the simple end-to-end tag maintenance, is not friendly to change in the network environment. In Vsaf, a hierarchical structure called AS community is designed to address the scalability changes faced by end-to-end tag schemes when deployed at scale. In Vsaf, AS can form a community structure with a hierarchy that splits the previous end-to-end tag maintenance between AS into a segmented cross-layer tag verification and replacement. The end-to-end direct trust is replaced with a cross-layer chain of trust delivery. In AS community, end-to-end tag is only maintained between AS with the same community. Traffic entering or leaving the AS community is operated by the border AS for tag replacement. Through hierarchical design, we can achieve the following three benefits. The first one, we can reduce the size of the tags maintained between AS. The second one, hierarchy effectively blocks external changes and provides scalability in large-scale deployments. The third one, cross-layer verification will filter malicious traffic as early as possible to avoid wasting resources. To simplify the tag replacement rules in data forwarding, Vsaf proposed a logical concept called virtual AS to maintain inter-community tags when entering and leaving a community, avoiding problems such as tag replacement difficulties due to multi-path transmission between AS or traversing non-Vsaf deployment areas such as S12. For example, S11 sends packets to AS23, and after passing through AS12, where Vsaf is not deployed, there are two different forwarding paths. At that point, since the logical AS community 1, virtual AS1 is set, the packets carry the same tag whether they are sent from AS13 or AS14. Both use the tag between virtual AS1 and virtual AS2. In the following, we further describe the general working process of Vsaf by example. Here, there are 9 boundary routers, router 1 to router 9, each representing one different AS, forming the AS community as shown in the figure. Router 1 sends out a packet to router 9. In the first step, router 1 learns that the destination is not inside that community by the destination address of the packet, but it is inside the trusted lines, and it puts the tag between itself and the virtual AS of this community, that is AS community 13, into the packets, and forming the tag route 1 to virtual AS 13. After that, the packets arrive at router 2. Router 2 as the boundary AS of the current community confirms by the packet destination address that the packet needs to be forwarded outside the community 13. So after verifying the validity of the current tag, the tag is replaced with the tag between community 13 and community 12. that is virtual-as 13 and to virtual-as 12. Similar to the above process, after the packet cross community 13 and reaches at the border ASO community 12, that is router 3. Router 3 will perform the same check and replace the tag with the tag between the community 12 and the community 11, and form the tag virtual AS 12 virtual AS 11. Next, the boundary of AS community 11 is reached, and the route 4 performs the tag check and the replacement the tag. Router 5, since this router is neither the source nor the destination of the packet, so it does need to do any processing and forwarding this packet directly. After that, it reaches the destination community and border as router 6 performs tag checking and replacement. The next one is router 7. Finally, it arrives at AS community 23. Router 8 performs tag check, after which the tag is replaced by the tag between route 8 and route 9 through the destination address, and route 9 receives it. And it will verify the tag validity and remove the tag and send it to the end host. So far, the data forwarding and verification process from route 1 to route 9 is completed, and the direct trust relationship between route 1 and route 9 is converted to a segmented trust delivery method. As a summary, Vsaf is a cryptography-based source address validation to guarantee consistent security benefits and provide scalability for different deployment scales and validation granularity. And Vsaf uses hierarchy and tag replacement to reduce overhead and improve scalability compared to traditional cryptography-based schemes such as SPM or IPsec. So there is some questions. The first, does Vsaf is prepared for IPv4 or IPv6 or both? For the limitation of IPv4 options header, it may be a problem for how Vsaf tag the tag to the packet, and to how to maintain and manage a hierarchy for Vsaf. Is it a distributed one or centralized one? And third, what IPv6 option header should Vsaf use? Destination, hop by hop, or routing option header? In our design, we use destination option header. And that's all. Thanks.
Thank you so much, and thank you for taking on the duty of presenting this work at very short notice. First up in the queue is Nalini Elkins.
Yes. Hi, this is Nalini Elkins at Inside Product. So again, I'll keep it to one question, which is, so say I'm Mr. Bad AS number 1, and my community is my friends, Bad AS number 2, Bad AS number 3. And we all say, yeah, good tag. And so what is I'm not understanding quite the validation mechanism. Are you intending for this stuff to be encrypted? Is there an external check, external root of trust? Can you explain more what this verification of tag entails? Yeah, thank you.
Can you hear me, by the way?
Yes, yes.
Nice. Thank you for the question. So first of all, this is Haiyan. I'm one of the collaborators of this research. So what you're asking is if there are bad ASs out there, how we actually validate those tags out there. Is that what you're asking? Yeah, that's actually a very good question. Yeah, that's actually a very good question. So talking about the ESAV, I want you guys to think about the autonomous systems, or let's say a set of autonomous systems as a daycare. Okay, thinking about those IP prefixes and IP addresses, they're like kids out there. Okay, those kids, they don't have driver's license, they don't have IDs. So our responsibility is to design a protocol that is running in the daycares to validate the identity of those kids. Okay, so basically what we do is that first of all, we don't search actually the actual routing table out there. We actually only need to check the destination IP prefix and to check if this destination is within the daycare or outside of daycare. If it's within the daycare, we send it to our intra-domain protocol. If it's outside, then we give this kid a sticker. We put that sticker on his head. And then we send this kid out. What you're asking is that what will happen if we have some evil daycares that does not care about those kids? The thing is that we are basically going to consider those autonomous systems as autonomous system that does not support ESAV. Okay, so first of all, this is not going to hurt the sender of the packet or the receiver of the packet. It is only going to hurt those evil autonomous systems who refuse to check the tag, if that makes sense to you. The thing is that our deployment, we don't require all the daycares to check those stickers. Okay, so for example, a kid is generated from a daycare with a sticker on there, and we are going to eventually have some not evil daycares that is going to check the validation of that sticker. I don't know if that makes sense to you. For example, if we have 3 autonomous systems, 1, 2, 3 connected out there, and the autonomous system 2 in the middle is evil or does not have ESAV deployed out there, it doesn't matter, because 1, 3 can still validate each other. And if you don't feel good or if you don't feel happy to join this ESAV system, you can ignore it. I don't think it's going to hurt our protocol. But still, that's a very good question.
Next up, Yuan Xiang Q.
Hi.
Yes.
Can you hear me?
Yes, I can hear you perfectly.
Hey, I'm from H3C. I have a question. Does Vsaf need to label all packets? Whether this additional overhead will have a significant impact on the efficiency of inter-domain transfers? Thank you.
Okay, so you're thinking about efficiency of the tag validation and tag generation. Is that what you're asking?
Yeah.
Sure. That's a very good question. Actually, we already test that on the commercial. We actually implemented the protocol and we actually test that on real-world routers we actually deployed that in a virtual router environment that is relatively a large-scale virtual network. I would say the efficiency, talking about throughput, we can achieve around 98% of the line speed with this kind of tag forwarding. So I don't think that is going to be an issue. And talking about latency, we don't have very detailed data out there, but the preliminary test showing that it is going to add in approximately 10 microseconds delay to the packet processing.
Okay, thank you.
Yeah, no problem.
Next up, Benjamin Schwartz.
Hi, Ben Schwartz here. I wanted to ask about the Mtu overhead first. What is the size overhead?
Very good question. So you're asking the size of our tag. Is that what you're asking?
Yeah, and any additional overhead associated with it.
Yeah, it's actually built in IP version 6 option header out there. The actual size. The thing is that we're not going to actually add extra header or extra information on top of the IP version 6 header, if that makes sense to you. So our tag is actually a part of the IP version 6 header.
Where
does that make sense?
Where does it go in the header?
The existing implementation is that we put that in the destination option out there.
Okay, but that's an extension header, right?
Yeah, that's an extension header. Yes.
So you know that extension header would not
just a little bit, not like a whole lot.
So how long is that tag?
I cannot remember exactly. It's like 64, I guess.
64 bytes.
Bits, yeah.
64 bits. So it's like an 8. So it's like a 64-bit Mac.
Yes.
Okay.
That's a very good question. Actually, the thing is that the existing implementation on IP version 6 is based on the extension, and we're also thinking about the adding that for IP version 4. That is probably also going to be added to the extension tab. That's a very good question. Yes.
Thanks.
So the overhead is around like 64 bits.
Thanks.
Yeah.
So my feeling about this is that I'm really interested to see something very much along these lines in terms of end-to-end cryptographic authentication of every packet. I think that's fascinating and worth investigating and investing in. I have disagreements with like every detail in this proposal. In particular, I really think that we should consider static setup instead of trying to do dynamic arrangements between the ASs, which creates kind of an n-squared problem where all the ASs have to talk to each other. I think we should consider a static cryptographic handshake setup. I think that would allow us to get rid of the hierarchy of communities, which is conceptually confusing, increases management. And I think that a big lesson from the TLS is that authentication is not really authentication without encryption is only half of the story. If you're going to do all the work to set up a shared secret between two parties, then you might as well encrypt the payload while you're at it. You now have the shared secret. So I would love to work with anybody who thinks that's an interesting direction to go in. And yeah, I'd be happy to be a part of that. Thanks.
Thank you. I totally agree with your comments out there. And I'm kind of making my answers short because we are running out of time yet.
All right. We are at the top of the hour, which means that we are basically running out of time. Questions that need to be answered in the subsequent period of time is what to do next. Is this are these protocols worthy? Worthy is not the right word. Is there sufficient interest to form a working group to progress the development of these protocols? Are the protocol concepts feasible in deployment on the internet? But I think we are pressed for time to address those in a thorough manner. I see Jared wants to. I guess we can spend another 5 minutes. Jared, you go first.
Yeah, real quick. Jared Mach as an individual. So I think that there's the opportunity for there to be some interesting work in this space describing this, but I think it also is going to pose some real challenges when it comes to actually deploying it, which is basically see everyone who's tried to either do BGP route filtering or BGP path scale, because a lot of these properties of this are going to scale similarly as those existing deployment efforts, and that is that has that takes a lot of compute resources, which quite often aren't going to be on these devices. Thank you.
Next up, Zen Ben Lim.
Okay. Zen Ben from Huawei. So from my point of view, I think that's in the presentation we I think that is agreed that there's the drawback of the existing source address validation solutions such as the Erpf, etc. It's truly worth to explore the possible solutions to these issues. But I think that the concern is the possible cost. From my point of view, maybe we think that we need to go on to discuss these possible solutions for these challenges. I think that maybe we need a venue for this point. Okay.
Thank you. Next up, Yan Xian Q.
I'm from H3C. As a vendor, all routers, switches, and gateway devices support URPF nor. URPF is a single point cell mechanism, and we agree that URPF is inadequate in addressing source address spoofing. I think DCell is a possible direction and seem worth doing. The benefit of DCell is that it can improve cell and does not need to modify packets during the forwarding process. In general, there's a lot of work to be done with intra and inter-domain cell. I support setting up a working group. Thank you.
Eric Finken, your turn, please.
Yep. So my name is Eric Weng. I am the responsible AD for this BOF, and I would love to thank the chairs and the speaker for the clear presentation. Now, we got the solutions, problem space has been presented. We were presented with two solutions. I wonder whether there is a third and a fourth potential solution to this. So in my opinion, I think it's a bit premature to think about a working group right now. But it's problem space that really needs to be explored indeed. And there is a mailing list, safnet@ietf.org. So I really hope that the conversation continues there. Thank you.
Yang Gao.
Hello, everyone. I'm from the China Academy of Information and Communications Technology. We believe that the problems raised by DCell are valid and important, and we are also doing tracking of related technologies. Compared with the previous technologies, DCell provides some more general solutions and is worthy of more efforts. We think it's necessary to promote the standardization of DCell in IETF. At the same time, we intend to carry out standard promotion in China Communications Standards Association. Thanks.
Thank you. We're now 5 minutes over. I would like to thank all participants, both locally and remotely. It is deeply appreciated that many people either went to bed very late or got up super early to be here virtually. The next place where we can continue discussion is the safnet@ietf.org mailing list. And this is where we can figure out whether to do another BOF, to initiate a working group, or to do something else. The mailing list is the next platform for discussion. Thank you all. This was a very exciting session, and I wish you a very pleasant day.